Good day, I'm Norman Wahlberger. Today we're going to start in the direction of calculus with integral polynumbers. We're going to introduce the idea of composition of polynumbers, which is an interesting operation that we can do with them, and then a rather special case of composition called translation. Although we don't have any pictures associated to polynumbers yet, it will turn out that these operations of translation do correspond to an intuitive understanding of moving things left or right. Then we're going to examine translation in a somewhat general way, and that will naturally lead us to the notion of a derivative. And not just a derivative, but also higher analogs of the derivative, which we're going to call subderivatives. These are subtly different from the higher derivatives that are usually introduced in calculus. So just the beginnings of calculus here in the very simple algebraic context of polynumbers. In fact, just integral polynumbers for now. Okay, so let's start talking about composition of polynumbers, and let's illustrate things with this particular polynumber. P equals 1, 3, 4, and in standard alpha form, that's the polynumber 1 plus 3 alpha plus 4 alpha squared. Then I remind you that we can evaluate P at a number C by defining P of C to be what you get when you replace the alphas with C's. So 1 plus 3C plus 4C squared. And since only elementary arithmetic is being used here, we can replace C with any, say, integer to get an integral value for P of C. So for example, if C is equal to 1, then the right-hand side here becomes 1 plus 3 plus 4, which is 8. Or if C was equal to 2, then we would have 1 plus 6 plus 16, which is 23. So P of 2 is 23. Or integral values also allowed, for example, minus 1, then we would get 1 minus 3 plus 4, which is 2, and so on. So today we're going to extend this idea by considering substituting not number values for C, but rather other polynumbers instead of C. So for example, suppose that we have Q, the polynumber 2 plus alpha. Then we could define P of Q, which is just this kind of expression here, but with the C replaced everywhere with Q. 1 plus 3Q plus 4Q squared. And explicitly, there's 1 plus 3, there's the Q, plus 4Q squared. And then we can just expand this out using our arithmetic for polynumbers and get 23 plus 19 alpha plus 4 alpha squared. And this new polynumber is the composition of P and Q. It involves both P and Q, sort of Q inside P. Before I move to the next slide, I'll just point out that the point of view that we're taking today in this lecture also is very much in line with this video in the Wildlin Alge series, Wildlin Alge 20, which is a video on bases of polynomial spaces. So if you'd like to get a little bit of another point of view on this topic with very similar kind of notation, then have a look at that video. All right, so we've defined composition of two polynumbers. So somewhat more formally, what we have defined amounts to this: that if P and Q are integral polynumbers, and if P has this particular form in standard alpha form, so A0 plus A1 alpha plus all the way up to AN alpha to the n, then what P of Q is by definition A0 plus A1Q plus A2Q squared, and so on, all the way up to ANQ to the n. We replace each of the powers of alpha here by the corresponding powers of q. Q is a polynumber, so the powers of q are just obtained by multiplying q by itself as many times as required. Alright, a little exercise. Show that in general, p of q is not equal to q of p. If you take two random polynumbers, p and q, then most likely p of q is not equal to q of p. So just make at least one calculation that shows that. But there are some interesting examples where p of q does equal q of p. And a very simple example is this one here. So suppose we define p sub n to be the kind of pure power alpha to the n. So in terms of our original notation, that would be a polynumber which has a whole bunch of zeros and then a 1 in the nth coefficient. So if we define p of n that way, then show that p sub n of p sub m is the same thing as p sub m of p sub n, and both of those are equal to p sub n times m. Another thing to observe is that if the degree of p is n in the general situation and the degree of q is m, let us say, then the degree of the composition p of q or the degree of the composition q of p, they're both equal to n times m. And to illustrate that, and so to suggest why it's true, let's have a look at an example. So suppose p is 1 minus 2 alpha plus alpha cubed, say, of degree 3. Suppose that q is equal to 3 minus alpha plus 2 alpha squared of degree 2. Then p of q would be, so there's p, we're going to replace each of the alphas with a q. So 1 minus 2, there's q, plus here, there's q all cubed. Now to expand all of that would be a little bit of work, but to figure out what its degree is not too hard. We're just looking at what's the highest power of alpha that will appear when we expand it all out. And the highest power of alpha will appear right here when we take that alpha squared term and end up cubing it. That'll have degree 6. On the other hand, if we look at q of p, it means we take the polynomial q, there it is there, and substitute p for alpha. So 3 minus, there's q, there's p, plus 2 times, there's p all squared. And if we wanted to know what the degree of that was, well, we would look for the highest power of alpha after we expand. There's going to be alpha cubes here and here. There's going to be an alpha cubed all squared. So there will be an alpha to the 6th when we expand that out. That'll be of degree 6 also. So that's just illustrating, giving you an idea of why this statement is true. So that's general composition, but today we're going to be looking at a rather special case of composition. So a very simple kind of composition. So the kind of simple composition that we're going to look at today is called translation. And that's what we get when we replace the alpha in a polynumber with the very simple polynumber c plus alpha for some integer c. So if we take our polynumber p equals 1 plus 3 alpha plus 4 alpha squared, then for example, p of 1 plus alpha, so the case when c happens to be equal to 1, well, you just replace alpha with alpha plus 1, or 1 plus alpha. Alpha squared replaced with 1 plus alpha all squared, and then we expand this out. Let's just do it once. So the constant term here, the 8, appears because you get a 1 here, a 3 here, and a 4 times 1 there for a total of 8. The coefficient of alpha is 11 because we get 3 alphas from here. When we expand this out, we get 4 times 2 alpha. So 3 plus the 8 gives us 11. And the alpha squared has a coefficient of 4 because that's only coming from here. When we square that, we get an alpha squared times that 4. So similarly, I'll leave you to check that if you replace alpha with 2 plus alpha, in other words, you get that expression there, then you get the poly number 23 plus 19 alpha plus 4 alpha squared. Or if we looked at p of 3 plus alpha, we would get 46 plus 27 alpha plus 4 alpha squared. The c can be any integer, so it could also be a negative number. For example, minus 1, then p of minus 1 plus alpha. Well, there's minus 1 plus alpha again. Expand it all out. Now 2 minus 5 alpha plus 4 alpha squared. And of course, the numbers don't have to be small ones. We could have p of 37 plus alpha, for example. Then we would have 37 plus alpha here and here. When we expand all that with a bit of arithmetic, we get 5588 plus 299 alpha plus still 4 alpha squared. Of course, we could do hundreds of different examples like this. These are all called translates of alpha because we're replacing alpha with the simplest kind of thing, essentially, which is not really a constant or an alpha itself, which is just alpha plus a number. Well, we like to have sort of official definitions for things and also some notation too. So this is an important enough idea that we're going to introduce some special notation for it. So our official definition is that if p is an integral polynumber and c is an integer, then the left translate of p by c is denoted by this. Capital L, standing for left, sub c, that's the amount that we're translating by, of p, that's the actual polynumber that we're translating, and that's by definition p of c plus alpha. We'll say that's left translation of p by c. Note that there's only plus signs here, so that in particular this is also defined if we had started with p a natural polynumber. In other words, all coefficients natural numbers. And c itself was a natural number. Then all the expressions involving here would just have natural number coefficients, so the sum, the translate, would also be a natural polynumber. So we could have done that. We could have started by defining translation for natural polynumbers and then extended it to integral polynumbers, but I'm just treating the integral polynumber as the main case here. Alright, so here's how the notation works. Here's p again. If p is that, then L sub 1 of p is p of 1 plus alpha. We've already computed that. Looks like that. And L sub 3 of p is p of 3 plus alpha. 46 plus 27 alpha plus 4 alpha squared. So in a few videos from now, we will be introducing pictures associated to polynumbers. But at this stage, the pictures are unnecessary. We're defining the left translate of a polynumber purely algebraically. Here is an easy and pleasant little theorem that tells us what happens if we translate a polynumber twice. First by c and then by, say, d. So if p is an integral polynumber and c and d are integers, then, so what does this mean? This is L sub d of L sub c of p. So it means that to evaluate this, we start with p, we apply L sub c to p. In other words, we translate p by c. And then once we've gotten that, we translate that whole thing by d. And the claim is that doing that is the same thing as translating p by c plus d all in one go. Alright, so the proof is not hard. Let's have a look at it. The left-hand side, L sub d evaluated at L sub c of p. So we replace the L sub c of p with what it's equal to, which is p of c plus alpha. That's what L sub c of p is. And then we have to take L sub d of that. We have to translate that by d. Well, that's going to be a polynumber in alpha. You can write it out as a bunch of alphas. And when we translate it by d, it means we replace each of the alphas by d plus alpha. So we can just as well do it right here. We can just replace that alpha with d plus alpha. So it's p of c plus d plus alpha. But the associative property holds. This is an integer, that's our simplest polynumber. C plus d plus alpha is the same as c plus d plus alpha. And when we read it like that, then we can see that that's just the translate of p by c plus d. So that's the end of the proof. And as an easy consequence of that, we see that if we translate by c and then translate by d, it's the same as if we first translate by d and then translate by c. Because in both cases we're getting the translate by c plus d or by d plus c, but since c plus d is equal to d plus c, they're the same. Alright, so here's an interesting idea. We had the idea of translating a polynumber by an integer c, perhaps by 1 or by 2 or by 37. The idea is to think about how this translate depends actually on c. So it means that we're going to translate p, but not by a fixed amount, but by a sort of general integer c. We're going to just substitute c plus alpha for alpha, where the c is just the letter c, representing some integer in our mind which isn't fixed. So that would be 1 plus 3c plus alpha plus 4c plus alpha squared. And then if we expanded this out, just treating this c like an unknown number for now, we would get 1 plus 3c plus 3 alpha. And then when we square this, we'll have c squared, so it'll be 4c squared. There'll be 2c alpha times 4 is 8c alpha plus 4 alpha squared. Now we want to think about that as a polynumber, so as a combination of powers of alpha. So we'll separate it into the things that don't involve any alphas, which is this term, and this term, 1 plus 3c plus 4c squared, plus the things involving just a power of alpha. So the 3 alpha and the 8c alpha can write like this, 3 plus 8c times alpha. And then the only thing involving a higher power of alpha is the 4 alpha squared term. So now it's a polynumber. There's some integer, there's another integer times alpha, plus another integer times alpha squared. So we observe that the 3 coefficients that we're getting here are themselves polynomials in C, whatever that kind of means. They're like polynumbers or like polynomials, except that instead of having alpha or beta, there's a variable c floating around. Not quite sure what that means. We observe that the degrees of these things are decreasing. This is of degree 2 in C. This is of degree 1 in C. This is of degree 0 in C. And also, important to observe that this first one, or the 0th coefficient here, is just p of c. It's just the original polynomial with alpha replaced with c. Well, that's not too surprising, because if you look at this equation, this is p of c plus alpha, here it is here. If we set alpha equal to 0 in both sides, then on this side we would have p of c, and on this side these two terms would disappear, we would just get this. So this has to be p of c. Nevertheless, that's important to observe. That thing is the original polynomial we started with, evaluated at c. But where do these things come from? Could we have predicted what those coefficients are? And what are we really doing here? It's not entirely clear, because we're starting to treat c as some kind of variable, We said we would try to be careful about not doing that kind of thing. Well, fortunately, we have a framework that allows us to say exactly what we've been doing here. It's the framework of polynumbers. So what we did on that previous slide is clarified by recasting it using polynumbers. And I remind you that we've talked about polynumbers. They are generalizations or extensions of polynumbers where we don't just have things going down in columns, or we don't just have things going along in rows, but we have a rectangular array involving both columns and rows. So for example, this is an unrelated example of a bipoly number. It's called Q. It's written in this rectangular kind of array. And we think of that as being a combination of alphas, sort of representing the rows, and betas representing the columns, with increasing powers of alpha going down and increasing powers of beta going across. So this can be rewritten as 1 plus 0 beta minus 2 beta squared, and then plus 3 alpha plus 4 alpha beta plus 0 alpha beta squared. And the alpha and the beta in this context are very particular kinds of, well, in this case, polynumbers. So alpha is 0, 1, and beta is 0, 1, this one being along a row, that being along a column. Okay, so that's what a bipolynumber is, just a quick review. And now what we're going to do is we're going to go back to that computation, and instead of using a variable c, we're going to just do bipolynumber arithmetic. We're going to replace the c with beta. This guy right here. So we're going to consider the left translate of p by beta. By definition, that is p of beta plus alpha. Well, beta plus alpha is the same as alpha plus beta, so we could also write it like this if we wanted to. And that's what we get when we take p, which I remind you was 1 plus 3 alpha plus 4 alpha squared, and we replace the alpha with beta plus alpha. So there's 1 plus 3 beta plus alpha plus 4 beta plus alpha all squared. And now we can expand that out, and we can collect terms involving the alpha squared, and the things that don't have any alphas in them. And we get the same thing that we did before, except there's betas now instead of c's. So we have 1 plus 3 beta plus 4 beta squared plus 3 plus 8 beta times alpha plus 4 alpha squared. But now we want to interpret this. This is a bipolynumber. So it means that it can be written as an array. So in other words, this is exactly 1, 3, 4, because those correspond to the powers of beta increasing with no alphas. And then this 3 plus 8 beta times alpha. There's 3 alpha there, and the 8 alpha beta is that term there. Plus 4 alpha squared is that thing there. And we agree not to put zeros here if we don't feel like it. Now, such a bipolynumber is very pleasant because prominently it's symmetric. The rows and columns are appearing symmetrically here. So we could rewrite it if we wanted to by writing it first in terms of this column. This column would be 1 plus 3 alpha plus 4 alpha squared. And then this column would be 3 plus 8 alpha all times beta. And this column here, plus 4 beta squared. So this expression and this expression are exactly the same, except the alphas and the betas have been interchanged. And the symmetry of this situation is not at all a surprise. It's obvious because we were evaluating something of the form p of beta plus alpha, or p of alpha plus beta. So the alpha and the beta here are appearing symmetrically. So of course we're going to get something that's symmetrical. This symmetry is a very important aspect of things. So notice that the original polynumber that we started with, p, here it is in sort of its original form, 1 plus 3 alpha plus 4 alpha squared, written as a column. That's appearing right there. That's the first column. And then there's sort of this other column, and then there's this next column, and it's not entirely clear how we get them, starting from this, because this is what we started with. But it's a very interesting operation to start with this polynumber and end up producing this little table, this array, this bipolynumber. To get a better sense of what's going on, let's have a look at a slightly bigger example. Here's another integral polynumber, q minus 4 plus 7 alpha plus 10 alpha squared minus 6 alpha cubed plus 2 alpha to the fourth. We'll translate it by beta, so that means evaluating q at the combination beta plus alpha. So there we have beta plus alpha substituted for all the alphas there. Now we have to expand this out, which is a pleasant task because it's just the binomial theorem applied several times. So there's minus 4 plus 7 beta plus alpha, 10, we're expanding beta plus alpha squared here, minus 6 expanding beta plus alpha cubed there, plus 2, there's beta plus alpha to the fourth. So I hope you recognize the binomial theorem there. You can have a look at the earlier lecture on the binomial theorem if that's unfamiliar. The coefficients here are the binomial coefficients formed by Pascal's triangle or Pascal's array. Okay, so our job is to expand this out and collect terms. So the first thing we'll do is we'll collect all the terms that don't involve any alphas. This minus 4, 7 beta, 10 beta squared, minus 6 beta cubed, and 2 beta to the fourth. There they all are. And then the terms involving a single alpha, the 7 alpha here, a 10 times 2 beta, 20 beta. There's a 3 beta squared times minus 6. And over here, 4 beta cubed times 2. So now reading across here, the terms involving alpha squared. There's an alpha squared there times 10, an alpha squared there times minus 18 beta, an alpha squared there times 12 beta squared. There's also an alpha cubed, which appears right there, coefficient of minus 6, and also right there with a coefficient of 8 beta. And last but not least, there's an alpha to the fourth times 2. So there's the full expression, and now we can associate to that the bipolynumber. It is a bipolynumber, and here is its array. Just the coefficients where we've dispensed with the alphas and betas. So minus 4, 7, 10, minus 6, 2 across that first row, then 7, 20, minus 18, 8, then 10, minus 18, 12, minus 6, 8, and 2. And if we want to know the alphas and betas associated to any term, it's just a question of reading down the rows and columns. So this one here, for example, is associated to alpha, alpha squared, alpha cubed. So there'll be an alpha cubed associated to that, and going across the betas, 1 beta. So altogether, alpha cubed times beta associated to that. Okay, so this bipolynumber, we're going to call it T of Q. It only depends on our starting polynumber. And maybe we'll give it a name. We might call it the Taylor polynumber, or probably better, the Taylor bipolynumber, associated to the polynumber Q. And notice again, very important, that it's symmetrical. The rows and the columns are symmetrically placed. Also notice that the original polynumber Q is right there along that first column. So let's have another look at this Taylor polynumber. There it is there again. I've just rewritten it. And now I'm going to write it out again, but reading essentially down the columns first. So there's the original polynumber Q, and there's the next column times beta, next column with a beta squared, next column with a beta cubed, and a beta to the fourth. When we look at the Taylor polynomial this way, we observe that the coefficients are starting with q, and then the other ones following are dependent on q in a certain way. And this relationship between q and these successive coefficients here in this Taylor polynumber is a very important one for mathematics. So this first one that appears is called the derivative of the original q. So there is q, and there is the derivative. And those of you who have done some calculus will recognize that it really is the derivative. If you take the derivative of this, the minus 4 is killed. The derivative of this is 7. The derivative of this is 20 alpha. The derivative here is minus 18 alpha squared. And the derivative of this is 8 alpha cubed. But the point is that we can define the derivative this way. We can say that if we start with a polynomial q, or a polynumber q, then its derivative is the next coefficient of beta in the Taylor polynumber associated to q. And that also suggests that these further or subsequent coefficients are also going to be important. And in fact they are, and we're going to give them names. You might think that they are just the higher derivatives of q, and that's almost true, but not quite. There's an important difference. So we're going to have to adopt some special notation and special terminology to describe these higher coefficients obtained from q. This next one, we're going to call it d sub 2 of q. And the next one, d sub 3 of q. And the next one, d sub 4 of q, and so on. And we're going to call these subderivatives of q. All right. So this is the derivative of q, and this is the second subderivative, the third subderivative, the fourth subderivative. So in terms of our notation, if there's the original polynumber q, then this column here represents, it's a column polynumber, which is the derivative, or we'll use the notation the subderivative. Putting a 1 there sort of tells us it's a subderivative. And this next column here represents the polynumber, which is the second subderivative of q, d sub 2 of q. The third one, d sub 3 of q, that's the third subderivative. D sub 4 of q is the fourth subderivative. And if the polynomial had higher degree, then we could keep going, that there would be more of these subderivatives. So next time we are going to talk about the relationship between these subderivatives and the higher powers of the basic derivative. This is a very interesting development. Okay. We are introducing calculus here in this purely algebraic framework. The derivative is usually introduced in calculus courses by first talking about functions, and then talking about secants, and then limits of secants being tangents. Then you have a tangent to a function at a certain point. You have to compute a slope, and then those various slopes at different points make up the derivative function. That's all rather complicated, and if you do it precisely, there's a notion of limit involved. And as we'll see later on, the notion of limit is in fact highly dubious. Okay. So the ordinary approach to derivatives is, first of all, very complicated, and secondly, logically weak. Here we see that, in fact, there's a purely algebraic approach which is dramatically simple. What have we done? We've started with the polynumber q, and we've evaluated q at alpha plus beta. And we just looked at what we got, and we see that when we expand that out, we see the original polynumber, and then the next coefficient of beta is the derivative. And then furthermore, for free, so to speak, we get the various higher subderivatives of the polynumber. So this is going to have a lot of implications that we're going to study next time. So you will not be too surprised to observe that the binomial theorem and that Pascal array or Pascal triangle somehow is intimately connected with this business of translating polynumbers and finding derivatives and higher subderivatives. So to get a sort of sense of how that goes, I propose that you give it a try, this exercise. So this is actually just some practice in going through the motions of this video and calculating the Taylor polynumbers for various polynumbers p. So by expanding p of beta plus alpha, find the Taylor polynumbers and the various subderivatives of p. So the first derivative or the first subderivative, same thing, and then the second subderivative, third subderivative, etc. And 4 different examples. This one p written this way, and then these ones with p written in the more original way. There, there, and there. This one is a kind of a pure power. If you, this one here is especially instructive because you can see very clearly, I think, why the binomial coefficients are playing an intimate connection with this subject. All right, so we have an entry point now to calculus, essentially a very elementary high school entry point, which is not tangential at all. It's actually very close to the heart of the differential calculus. Euler and Lagrange would not have been surprised at all by this point of view because they also thought very algebraically about derivatives. So next time we're going to do some calculus with integral polynumbers. I hope you'll join me for that. I'm Norman Weilberger. Thanks for listening.